Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on the hot topics in materials research. My name is Elizabeth Wilson. Advances in quantum entanglement, quantum cryptography, and quantum computing require good sources of single photons. One-dimensional quantum dots and three-dimensional carbon nanotubes have been explored for their single photon emitting properties. But in the past decade, scientists have begun to study two-dimensional materials. Monolayers have advantages, such as scalability, strong tunability, and possibility for monolithic on-chip integration in devices. But they also come with problems. The inherent defects that litter their surface produce crowds of photons with different energies, leading to very complex, craggy spectra with too many emission lines. Now, a serendipitous chemomechanical discovery has allowed postdoctoral researcher M. Iqbal Bhakti Uttama and colleagues at Northwestern University to develop a coating on a 2D material that suppresses the production of unwanted photons, allowing single photon production with greatly simplified spectra.
The problem the paper is addressing is that if you simply use this type of structure, there can often be too many defects that emit simultaneously within a single training site.
2D van der Waals materials, such as hexagonal boron nitride and tungsten diselenide, are popular with materials scientists for single photon emission studies due to their unique atomically thin morphology and electronic structures. And while coated nanotubes are able to produce single photons with similar energies, two-dimensional materials are much more versatile. They're prepared more easily and can be readily integrated into chip manufacturing processes. Uttama's group works with tungsten diselenide monolayers. While casting about for surface modifications that could potentially suppress the production of unwanted photons, they hit upon the idea of using aryl diazonium compounds. Aryl diazonium chemistry has been used in the past to functionalize the surface of carbon nanotubes. And as it turns out, Uttama's group found, this chemistry also works for tungsten diselenide surfaces as well. The group immersed tungsten diselenide monolayers into an aqueous solution of 4-nitrobenzene diazonium tetrafluoroborate. The electrophilic molecules withdrew electrons from the monolayer, creating aryl diazonium radicals. These radicals react with each other to form nitrophenyl oligomer chains. And instead of binding covalently to the monolayer surface, the oligomers form an add layer that is physisorbed on the tungsten diselenide surface. The spectra of photons generated when they irradiated the coated surface was vastly simpler than the uncoated monolayer.
We are quite delighted at seeing our experimental results because we see that this can be actually useful for future experiments that we want to do.
So what is the add layer doing to suppress unwanted photons? Photon emission occurs via the decay of an exciton. An exciton is a quasi-particle composed of a negatively charged electron and a positively charged hole pair. When an exciton collapses, a photon is emitted. Two material properties, defects and strain, are crucial for the production of excitons and thus photon emission. Defects commonly involved in single photon emission are atomic point defects, where one atom is missing. The strain between bonds, which often accompanies defects, can do things to electronic structure, narrow band gaps, for instance. Defects and strain combined generate electronic environments necessary for photon emission to occur. Density functional theory provided insight into how the add layer simplified Uttama's group's photon emission spectra. It turns out the aryl oligomer add layer generates energy states that are in resonance with many tungsten diselenide defect states. This quenches the photon emission pathways, leaving much fewer photons with different energies and hence a simpler spectrum. On a strained surface, there can be variations from location to location and sample to sample. So there's work to be done in targeting defects that aren't resonant with the ad layer. In that vein, there's rich territory to explore, Utama says. This strategy can be generalized to other 2D photon emitting systems. He wants to expand control of photon emission with different ad layers that target certain emission pathways. For example, Utama envisions perhaps placing 2 different ad layers on a surface, one on top and one on the bottom, to further tune a layer's photon emission properties. This work was published in a recent issue of Nature Communications. My name is Elizabeth Wilson from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.